without further ado, I give you Leslie Lamport. Thank you.
Okay, thank you. Is this working? Yes, it is. Amazing. Okay. Oh, well, nothing works.
Is that a Lamport clock?
No, unfortunately. Okay. Oh, fine. Lost that. Okay. What this talk is about, I'm afraid it's not going to be about distributed computing. We'll talk about concurrency, as obviously as some of you expected me to say. Because I have nothing new to say about that. I'm just tired of saying the same old stuff. But I've realized that some things that I've learned about writing concurrent programs apply to all programs. So I'm going to talk about programming today, which I think is something that will interest you all. Algorithms. Now, I'm here because I wrote concurrent algorithms, not concurrent programs. And an algorithm is not a program. It's a higher level, more abstract thing than a program. It can be implemented in many different programming languages. And we don't have to write a algorithm in a programming language. And in fact, we shouldn't write algorithms in a programming language. Because programming languages are complicated, for a good reason. They have to be efficiently executed, and they have to handle large programs. But algorithms neither have to be executed, nor are they usually large. So what languages should we use? Don't get hung up on languages. Programming people, computer people are just much too hung up on languages. You should think about ideas, not about the language they're expressed in. Now, concurrent programs, they're ones that contain multiple threads of control that can be executed, and the multiple threads can be executed concurrently. Now, distributed programs are concurrent programs in which the threads can be executed on different computers. So distributed is just a special case of concurrent. Concurrent programs are very hard to get right because the actions of different threads can be interleaved in many different ways. And that implies that there are a huge number of possible executions. It's hard to think of all the ways that things could go wrong with such a huge number of executions. And debugging doesn't work. You can't be sure that with debugging, you can't be sure that you've checked all relevant cases because there are so many of them. And a program may work fine. You may have tested the hell out of it. It may be working fine. And then a change that alters in the system somehow that alters the relative execution rates of the threads can reveal a bug that was never revealed in years of execution of the program. And fixing one bug is likely to introduce another one. Debugging doesn't work. So how to write a concurrent program? First you figure out what part of what the program does involves concurrency. Now, it's the part, basically, that synchronizes the threads, that makes sure that they all work together and don't step on each other's toes or anything. And it's usually a very small part of what the program does, but it's a very important part. So what you need to do is find a correct algorithm that does that part. Now, maybe this algorithm is one you could find in a textbook. Or maybe it's one that's similar to something you find in the textbook, but you may need to modify it a bit. That's fairly common. And it may be brand new. And it's hard to get a concurrent algorithm right for the same reason that it's hard to get a concurrent program right. But algorithms are simpler than programs. So we've got a fighting chance of getting them right. And once you've got a correct algorithm, you can then implement that algorithm. You may still have coding errors, but you'll know that what you're basically trying to implement is correct. And coding errors, I'm not interested in coding errors. Lots of languages and tools have been developed for coding, for catching coding errors. And programmers are really good at coding, but they're not so good at finding correct algorithms. So, how do you find these correct algorithms? Well, important thing to think about is abstraction. Something is usually called an algorithm. Remember, an algorithm is something that's more abstract than a program. And something is usually called an algorithm only if it can be useful in many applications. Otherwise, nobody would put it in an algorithms textbook. Now, the algorithm that describes how concurrency is implemented in a program is often useful only for that program. So it's usually not called, is this thing coming on me? It's pretty choppy. Yeah, whoever is doing something, please either turn it on or turn it off. Instead of calling what is an algorithm, I would call it an abstract view of the program, or maybe an abstract program, or maybe simply an abstraction.
Backup mic.
Okay, well, I'll try to stay put here. So, how do we write a concurrent program? We find an abstract view of the program that describes how it handles concurrency. And it's at a higher level of abstraction than the code. And programmers are taught how to code, but not how to abstract. And abstracting involves a new kind of thinking. Thinking before you code. Thinking at a higher level than code. Programmers should learn how to do it for all programs. So what's a program? By a program, I mean any piece of code that requires thinking before you code. It might be a complete program. It might be a method in some class. Or it might just be a complicated loop inside of a program. It's any piece of code that requires thinking before you code. And it's any piece of code that to be used by someone who doesn't want to read the code. So how do you write an abstraction? Well, programs are written for many different purposes, and there's no method that's going to work for all programs. For most programs, you should write two things: what the program does and how the program does it. So what language should we use? Again, don't get hung up on languages. If we want to build a tool to check that the how implies the what, then we need a precise language. And precise language is really needed to ensure that a concurrent program does what it should do. Because remember, concurrent programs are really hard to get right. And I designed TLA+. It's a language, precise language for describing concurrent algorithms, abstract views of concurrent programs. But it's not needed for most programs. And I'm going to give you a trivial example of a program. To write a function that computes the largest element in a 30-bit array of integers. Sort of a trivial programming task, but that's a programming task. And it's too simple to require much thinking before coding. If I were really compulsive, I might write something, the what, return the largest element in an integer array A. How? we'll examine a of 0, a of 1, et cetera in turn, letting x be the largest value that you find, and then return x. And here's that code written in Rust. By the way, I don't know Rust. I got a colleague who does know Rust to write this. So he tells me that this is a Rust encoding of that how. And raise your hand if you see the bug in this algorithm. Oh, I see about 3 people raise their hands and see the bug. It's not a coding bug. It's a bug in the what. And what's the bug? The what is return the largest element in an integer array A. But if A has no element, then there is no largest one. So this what is incorrect. It can't be implemented. And there's an obvious fix to the what. You say either that or you return some error value if A has no elements. And then the obvious fix to the how, you add this red stuff to that Rust code. But we're going to use abstraction. And let's see how abstraction removes coding details and helps us understand why the program does the right thing. And if I can simplify, such a trivial example, imagine what abstraction can do when things get complicated. But again, I have time only for a trivial example. And we really wouldn't use this in such a tiny example. But it illustrates how abstraction works. So, first of all, it says return the largest element. But function call and return is a coding detail. It's not an interesting part. We're interested in how the largest element of A is found, not how we return that value or how we get A. So I'll simplify the what by simply set x to the largest element in an array, of the integer array, or blah, blah, blah. Well, why just integers? We let A be any array of numbers. So we don't have to specialize it to integers. There's nothing special about integers. Any old numbers will work. And why an array? I'm assuming that we're interested in the elements and finding the largest one of the elements, not in how they're arranged. So instead of an array, we'll abstract that to a multiset of elements. And it's a multiset, not a set, because it can contain multiple copies of the same element. Now, I don't like this part of the what, because it complicates the code. And I want the code to be as simple as possible. So can we find a different what that's just as good, but has a simpler implementation? Now, of course, this is silly for such a simple example. The complication is 2 lines of code. But when I wrote I used to do some code programming in my day, and often I would decide what I wanted the program to do. And then I realized that coding it would be a lot of work. And I'm as lazy as the next guy. And what I would do is figure out what I really needed the program to do. And the result was a what that might not have everything I wanted, but had everything I needed. And this took time. I would spend a fair amount of time thinking about this what. But it saved much more time when it came time to write the code, much more than it took me to find a simpler what. So finding the what, it's extra work, extra thinking, but it saves a lot of time in the end, because it produces something. It can produce something simpler in real examples. Now, what I want to do is eliminate this, which requiring this. Now, how to do that is not obvious to most programmers. And it's obvious to me because I was educated as a mathematician. So I know what the largest element of an empty set should equal. And here's how. Instead of setting it to the largest element, I set x to the smallest number that's greater than or equal to all the elements of A. Now, the two are equivalent if A is not empty. But what if A is empty? It means if A is empty, then what we have to set x to is a value that is at a number that's greater than or equal to all elements of A. So how do we do this for the empty set? Now, if I claim that I'm richer than everyone living in Bodie, California, I'm also poorer than everyone living in Bodie, California. And the people who are laughing realize that's because nobody lives in Bodie, California. Another way of saying the same thing is there's nobody living in Bodie, California that's either richer or poorer than me, because there's nobody living in Bodie, California. Now, this is simple logic, but it's actually mathematical logic. And to think rationally, you have to understand simple logic. And programmers should think rationally. So you all should know simple logic. So if A is empty, then we need a number that's greater than or equal to all to the empty set of elements. Then that means if A is empty, we have to set x to the smallest number. Now, mathematicians sometimes define minus infinity to be the smallest number. So we'll take this to mean that this what implies that if A is empty, then x is set to the number minus infinity. Now here's the how. We let B, some new array B, equal to the given array A, and we let x be minus infinity. Then while B is not empty, we let I be any element of B. Now notice this is a non-deterministic program because there are many possible different executions depending on what value you choose for I. Then we let B be B with I removed. And if I is bigger than x, then we let x equal to I. Now, notice I used an ad hoc combination of programming language notation and English, which is generally what I use for doing something when writing a program, a non-concurrent program. And most of the programs that I wrote were non-concurrent. But now, how can we convince someone that this implements the what? Now, I believe that most programmers could only show that some executions compute the right value of x, but would have no way of knowing how to prove that all possible executions produce the right value of x, which was what we want to show to make sure that this algorithm is correct. Because remember, there was just one value, had to choose the particular value of A that would reveal the bug in our original what. So how do we know there isn't some other value of A that would cause this algorithm not to work? Whoops. Now, seeing how to do this requires thinking about executions. So let's think about executions. What is an execution? An obvious answer is that it's a sequence of steps, where each step is the execution of some part of the code. Now, usually a better answer, and I say usually because no rule applies to all programs, but usually a better answer is a sequence of states. An execution is a sequence of states. And a step is a pair of consecutive states. We'll see later why this is a better answer. And this step is a pair of consecutive states that describes execution of a part of the code. And to see how we describe an execution this way, let's look at one possible execution of our simple algorithm for computing the the largest element of A. Now, I'll suppose for an example that A is the multiset that has 2 copies of 2 and 1 copy of 3, which we might write in any of these 3 different ways. I'll write it this way for no particular reason. So we let B be this particular value and X be equal minus infinity. So a state will describe the value of B and X and maybe some other stuff. We'll worry later about the other stuff. So I'm just going to show the values of B and X in each of these states of the execution. So what are their initial values? Well, an obvious answer is there's some standard, assume we have some standard initial value, let's call it question mark. So we can set B and X both equal to question mark. And we first execute this statement, and an obvious execution is represent this execution in 2 steps. The first step sets B to this multiset 2, 3, 2. And the second step sets it to X to minus infinity. But to understand this abstract program, we want an execution to be as simple as possible. Simplicity, simplicity, simplicity. And this means making an execution have as few steps as possible, which will still help it be an accurate enough representation of what this program, an accurate enough abstraction of what this program does. And these 2 steps are of no interest. So instead of calling those 2 steps, let's just let the initial state have those particular values of B and X. And to say that that's what I'm doing, instead of calling that a let statement, I'll say this is initially an initially declaration. So we declare those to be the initial values of B and X. I mean, you know, this is pseudocode that can mean anything I want it to mean. Again, the important thing is we want to understand the executions. We're not worried about, you know, as long as we understand what this means, then it's fine. Okay, so what's the next state? Well, code doesn't tell you what constitutes a step. Is executing this assignment to I 1 step, or is choosing the element in B 1 step and setting the value of I another step? Code doesn't tell you what constitutes a step. So to keep the abstraction simple, what I'm going to make a single step is evaluating the while loop's test and evaluating its body. Make that all 1 step. If you think about it, that's a good abstraction. It's good enough to know whether, you know, we're doing the right thing and how we're computing the largest element in A. Now, I won't bother defining a way to make the pseudocode say that that's all 1 step, just as long as you know. So executing the next step can let I equal either 2 or 3. And let's just choose, so the execution lets it be 3. So that executing its step, B is not empty, so it lets I be an element of B. It removes B from I and sets X to I if I is greater than X. But 3 is greater than minus infinity, so we set X to 3. And the next 2 steps both have to choose 2, because that's the only value left in B. So it's clear that the first one will remove 1, 2 from B and leave, and set X to 2. No, I'm sorry, it should leave X equal to 3. Yeah, I worry about the spelling of each thing in the example, but don't worry about minor different things about whether the example is actually correct. Sorry about that. So the next 2 that I have to choose to, oh, I'm sorry, no, it is right. It is wrong. If I is greater than X, yeah, let X equals, oh, so it should leave X equal to 3 in all of those steps. Okay, fine. Sorry. So the next step finds B empty, so it exits the loop without changing B or X. And so this is the complete execution. But that last step is uninteresting. So instead, what I'm going to declare that the execution terminates when this while loop finds B equal to the empty set, the empty multiset. And so that's my definition of the execution. Now, I don't know how to say that with code. I mean, I could invent some way, but as long as you know that that's what it means. I mean, this execution is going to stop as soon as B becomes the empty set. And that's easy. Actually, it's very easy to say that in TLA+. But I'm not going to bother about that. And again, don't hang up about languages. Understand what we want the set of executions to be. Okay, now what's a state? Now, for executions to be a useful way to think about a program, the possible next states must depend only on the current state and not on any previous state. We can choose states this way for abstractions that describe actual programs because programs are executed on computers. And what a computer does next depends only on the current state of the computer, not what it did in the past. And perhaps external inputs, but it doesn't depend on previous states. So we should be able to write our abstraction in such a way that what it does next doesn't depend on any previous states. And for this example, the state only has to describe the values of B and X. The variable I is used only to indicate how the step that ends in the current state changes the value of B. The value of I in previous states doesn't influence what the next state is going to be. And had I not eliminated that extra step at the end, then the state would also have to have indicated whether the execution had terminated. So there had to be something else in the state to say whether, when B is empty, whether or not the program is terminated or not, whether the execution is terminated or not. But that's the reason why I wanted to remove that extra step. So I wouldn't have to add any extra part to the state, because we want the state to be as simple as possible. So now we can answer the question of why is the abstract program correct? Why does any possible execution terminate with X equal to the correct value? Well, at any point in the execution, what can happen in the future can depend only on the current state. Therefore, at any point in the execution, the value X that X could have when execution terminates can depend only on the current state. Why X could only have the correct value when it terminates must depend on something that's true of every state. Something that's true of every state, of every execution of an algorithm, is called an invariant of the program or the algorithm. You don't understand why a program does the right thing, for example, terminating with the right answer, unless you know the invariant that ensures that it does the right thing. Here is an invariant for our example, where I'm defining max of M for a multiset M to be the smallest number that's greater than or equal to every element of a multiset M. So I'll just define max of M to have that meaning. So the program should terminate with X equal to max of A. That's what correctness means. And this is the invariant. It says the max of the multiset containing the two elements, x and max of b, is equal to max of a. A beautiful, simple invariant. Why is it? And to show that this is invariant, we must show that it satisfies two conditions. First, it has to be true of the initial state. And second, if it's true in any state, then it must be true in the next state. Now, if those two things are true, then obviously it's going to be true of all states of any execution. So it'll be an invariant. And to show that the invariant implies correctness, we want to show the third thing, that it implies that x equals max of a in a terminated state. Well, why is it true in the initial state? Well, it's because in the initial state, b is equal to a and x equals minus infinity. So that condition becomes max of minus infinity of max of a equals max of a, which is true because the max of minus infinity and any number is that number. Now, why does it imply that x equals max of a in a terminated state? Well, in the terminated state, b is equal to the empty multiset. So, and the max of the empty multiset equals minus infinity. So that condition means that max of x and minus infinity equals x, which is true because the max of any number and minus infinity is that number. So 1 and 3 are simple. But what about 2? I don't know how many programmers can figure out why this condition is true. I believe you should learn how to show that this condition is true. I don't have time to teach you how, but it's a really important condition to understand because understanding why something is an invariant is very important. And I think you should learn how, because I expect that those people who can't do it are going to be among the first programmers replaced by AI. So learn it. Termination. I explained how to show that x has the correct value when the abstract program terminates. But I haven't explained how to show that it always terminates. I don't have time to discuss termination. If I did, we would see that the program doesn't terminate for some values of a. Can anyone see what values of a those are? Just raise your hand. No one can see it. One person. Okay, 2 people. Well, okay, that's a homework problem for you. Figure out what values of a this algorithm does not terminate. Okay, how do we implement this? How do we implement minus infinity? Well, suppose a is an array of 32-bit integers. Method 1, we can implement minus infinity as the smallest 32-bit integer. If that's acceptable, namely you don't care whether between whether the value is minus the smallest negative representable integer or a is empty, then that's fine. That gives us a simpler implementation. Method 2 is you simply implement minus infinity as an error value. And the Rust code that tests if a is empty that I showed you actually implements that abstract program when minus infinity is the error value. But few programmers, and in fact few computer scientists, know what it means for a program to implement an abstract program or an algorithm, to give a precise definition of that. I don't have time to do it now, but it can be done. And in fact, TLA plus, gives a precise definition of what it means for when TLA plus abstraction to implement another TLA plus abstraction. And all you have to do is represent your program in TLA plus, and you know what it means. I don't have time to explain. Now, real concurrent programs, the why and how should be precise. Tools should check that the how implements the why. And here's an example of how TLA plus works in practice. Amazon Web Service wrote this paper, the people in Amazon Web Services. You know, they're the people who implement the, all the web stuff in Amazon. They wrote this paper, and they're the ones that build Amazon's cloud structure. And it talked about web services using formal methods. The formal method they used was using the TLA plus language to write their abstractions. And here's what they say, the key insights. Using TLA plus found bugs in system designs that can't be found through any other technique we know of. Formal methods are surprisingly feasible for Main Street software development and give good return on investment. These guys are practical businessmen. And writing that TLA plus specification takes time. And they believe that it's worth taking that time in real dollars and cents because it avoids bugs. And they say at Amazon, methods are routinely applied to the design of complex real-world systems. This was written, God, it must be almost 10 years ago now. I believe they're still using it, but I don't. As of a couple of years ago, they were still using it, but I don't know what they're doing today. But I presume they're still doing it. And it says, TLA plus finds bugs in system designs that cannot be found through any other technique we know of. These are fundamental design flaws. They're not just simple coding errors. Very expensive to fix after the code is written because it requires extensive recoding. And often, the bug isn't found until the code has been released to users, which is considered as a disaster if you're Amazon. And Amazon engineers find these flaws before any code is written. Now, is abstraction useful just for concurrency? Now, the code for concurrency is important. Handling concurrency is important, but it's a small part of the code. What about the rest of the program? Well, I know of only one case in which an entire system was built starting from a TLA plus abstraction of the entire system. Rosetta is a European Union spacecraft, and that explored a comet, and several of its instruments were controlled by a real-time operating system called Virtuoso. And Virtuoso people decided to write a new version of that system starting from scratch, and they wrote a book about it, how they did it. And they did the high-level design in TLA+. And here's an email from the head of the development team that I didn't know they were doing that. I learned about it after they had published the book. He wrote to me in an email that the TLA plus abstraction helped a lot in coming to a much cleaner architecture. He said, we witnessed firsthand the brainwashing done by years of C programming. I call it mind rot rather than brainwashing, but I think that's what I would call it. And one of the results was that the code size is about 10 times less than it was in the previous system. And everybody knows when you build the second system syndrome, the second system is always much larger than the first one. But it's actually the code was 10 times smaller. And you don't produce 10 times less code by better coding. You do it with a cleaner architecture, also known as a better high-level design, a better abstraction, which comes from thinking about an abstraction, not about the code. It doesn't come from thinking in a programming language. So sometimes what a program should do can't be stated precisely. So here's an example I encountered. In writing the TLA plus, a pretty printer for TLA plus, and if the input, TLA plus, you write the input in ASCII, and actually alignment is important. The meaning of alignment of these and signs is important. And the naive output would produce this, because in the naive output, you don't write everything, for pre-printing, you don't want to use fixed width font. And so you get something like this. And the user probably wanted these two pieces of it aligned. And so that would be the right output. On the other hand, if you looked at this input, the naive output would be like this. And that's probably the right output because the user probably didn't want these things aligned. So that's correct in this case. So there's no precise definition of correct alignment because we can't describe precisely what some unknown users wants. So if we can't describe what precisely, abstraction is useless, right? Obviously, wrong. The program has to do something. And not knowing precisely what it should do means we have to think abstractly about what it will do. And it's impossible to specify the best printing printer because there's no such thing. But the program has to do something. And writing stream of consciousness code doesn't produce a good program. So what did I do? What was my abstraction? I wrote 6 rules plus definitions, and those appear in comments in the code. And for example, it says a left comment token is left comment aligned with its covering token. Well, that means nothing to you, but the meaning of something like left comment aligned, it was defined precisely, but in English. Maybe an equation or something else. And why did I write this abstraction? Because it was a lot easier to understand and debug 6 rules than 850 lines of code. And I did a lot of debugging of the rules, aided by debugging code to report what rules were being used. And the few bugs in implementing the rules, they were trivial, easy to catch. Had I just written code, it would have taken me much longer and would not have produced formatting as good. So what's typical about this abstraction? It's at a higher level in the code. I could have implemented this in any language. And no method or tool for writing better code would have helped to write this abstraction. And no method or tool for writing better code would have made the abstraction unnecessary. It says nothing about how to write the code. You write an abstraction to help you think about the problem before you think about the code. What's not typical about this abstraction is that it's quite subtle. Perhaps 95% of abstractions require much less thought, and the shorter and simpler abstractions suffice. And it's a set of rules. And a set of rules or requirements or axioms is usually a bad abstraction because it's hard to understand the consequence of those set of rules. So I had to do a lot of debugging about those rules. But it was the right abstraction for this problem. And no method is best for all programs, as I said. And this was an unusual program in that respect. Thinking is always better than not thinking before coding. Now, some people say that you shouldn't think too much before coding. I suppose there are some cases that's true. But I will tell you that too little thinking is a much more serious and much more common problem than too much thinking. And how to think? Well, write. Writing is nature's way of letting you know how sloppy your thinking is. That's a cartoonist. Gwynedd was a cartoonist, and he wrote that in some cartoon. And my statement is, if you think without writing, you only think you're thinking. Writing helps you think better. But thinking helps you write better. Thinking better helps you write better. So it's a virtuous cycle. The more you write, the more you have to think, and the better you make better thinking, and the better you're thinking, the better your writing is. To begin with, most people must learn to write better. And this means writing to convince others. It's much too easy to convince yourself of something that's not true. And you have to learn to read what you wrote the way others might read it. Perhaps others read it, reading what you've written. You could ask them, what you think this means, and you can see where you've written something that's ambiguous. And how to think abstractly, Well, abstraction is what I'm good at. And being good at it is why I was invited to speak to you. And how did I become good at it? In large part by being educated as a mathematician. Abstraction is at the heart of math. Math abstracts from 2 sheep and 2 goats to the number 2. That's what math is all about, abstraction. And I don't know how you should learn to be better at abstraction, because in math, it's mathematics. TLA Plus teaches some users. I've seen that users who write TLA Plus, it teaches them to be better at abstraction. But that TLA Plus may be too hard for most programmers. I don't know. But perhaps mathematicians can teach abstraction by making it, rather than the math itself, the subject. I don't know. Try asking them. So things to remember. Programming should be thinking followed by coding. Thinking requires writing. And if the program is simple, very little writing is necessary. But it takes thinking to know if it's simple, and therefore it takes writing to know if it's simple. For non-simple programs, abstract thinking above the code level can avoid errors and lead to better, easier to write code. And a non-simple program can be anything from a complete system to a complicated loop. No way of abstracting is best for all programs, but the abstraction of an execution as a sequence of states is most often a very good one. So that's a good way to start thinking abstractly about your programs. And a state should contain all the information that can affect what future states are possible. That is all except external inputs, which you can think of as simply, in terms of thinking about the program, you can think of a program that depends on a user input. You can think of it as just making an arbitrary choice and not worry about why it made that choice, whether it made it itself or it was made because of some input from the user. Doesn't make any difference about how you think about the program. In this approach, abstraction, a program does the right thing because it satisfies an invariant. And understanding the program requires understanding that invariant. And remember, don't get hung up on languages, especially not on programming languages. Now, this has taken longer than I expected, and I can stop now and then take some questions, or I can run over and talk to you about why programs should have bugs. So, who would like me to run over and? Okay, why programs should have bugs? Well, I started programming in 1957. And I can write, people write much more complicated programs now than they did then. And part of the reasons is better programming languages. But the major reason is because we now have libraries of programs that our programs can use. You know, when you read about Java, I mean, Java used to do most of my programming in Java, and the thing, I didn't worry too much about the language. It was, all of the different standard methods that came with it. The hardest part of programming is now figuring out how to use these library programs, because many of them can never have bugs. Because a program can have bugs only if there's a precise description of what it should do. And part of that description is language dependent, and that part is usually very simple. And it's often implied by just how the program is called, especially for strongly typed languages. But the most useful programs do complex things, and you shouldn't have to read the code to understand those things. They should have an abstract, language-independent description. And few programs have such a description. Many have no descriptions at all. And I won't bother giving you the horror stories of how this has made it difficult or impossible for me to use some library programs. I mean, with the absolute crap that they claim to this documentation is. But instead, I'll tell you about an organization that did a pretty good job of providing precise descriptions. It was the W3C. W3C is the World Wide Web Consortium. And they wrote a JavaScript standard. And now there's been a lot of work in verifying that what a program should do is implied by how it does it. And initiated by a 1967 paper by Robert Floyd. But most of that work views what a program should do as a relation between its inputs and its outputs. It tells you if you give it this input, here's what the output will reproduce. And that's the view that was used by the W3C standard. And this view works very fine for most sequential programs. And I expect most JavaScript programs are sequential. But in 2016, I produced a video course, you can find it on the web, about TLA+, along with web pages for viewing it. It's really cool the way it allows you to make use of the videos, to stop the videos at the right place and download something and stuff like that. And the users, viewers of that, use the web pages to view the course, interact with a JavaScript program. And it's a concurrent program because the code controlling the video is executed by one thread, and the code handling mouse clicks is executed by a different thread. And executing a library program can change different parts of the state at different times. And the order in which those changes occur matters, makes a difference to the program. And it can't be described by viewing what the program does as a relation between inputs and outputs. That's why you have to view it as an execution, which is a sequence of states. And the hard part of writing my JavaScript program was figuring out how to get the library programs to interact correctly on all popular browsers. Well, 3 popular browsers is what I used. It required a lot of debugging to use those JavaScript methods. And it seems to work correctly, but there's no way to be sure that it will keep working correctly. And we should be able to do better than that. Okay, that's it.
So, thank you for joining us and helping us wrap up this this week of fun open source. Are you still open for doing a couple of questions?
Sure.
Cool. While I think we've got one in the front row, but just before we get into that, I also wanted to thank you for joining us. And we've got and becoming a member of the SCaLE family. So we've got a jersey there for you, just like all our staff wear. And we hope you'll wear it with pride.
Great. Thank you.
So it looks like we got a question in the front row here with Chris.
Sure. You mentioned that abstraction is hard for programmers to learn, and most of them, don't know it right now. It'd be great if they did. And I was thinking, my math professor used to describe computers and computer science as essentially the mechanization of abstraction. It makes me think, like, AI models pretty much live in an abstract world already, and we've already got model validators and provers that can check stuff. Is it maybe easier to outsource the abstract thinking to the machines?
Well, I don't know what you mean. I've never heard. I know nothing about AI more than, you get by reading the newspaper. Sorry. Yeah, I said I know nothing about AI other than what you can probably read by reading Science News and the New York Times. But I don't know what kind of validators for AI programs there are, because AI it's a really serious problem if you're trying to use AI to build systems that are reliable. And the whole thing about AI is that it solves problems that we don't know how to solve by writing programs that we don't understand. So we don't know what they do, and how to make these AI programs, reliable. That they satisfy certain precise conditions, like not running over children. I mean, that's that's a big open problem, and if I were just starting out, that might be a problem I would be interested in. But I've retired.
Leslie, thank you for your lifetime of work. Thank you for your lifetime of work, both in computer science and in writing open source software, such as LaTeX and TLA+. My question for you is, your generation of computer science academics were closely linked with the world of open source even before we called it that, and implementing the tools you needed and the ideas that you had as open source software that you shared with everybody on the internet. The generations of academics behind you have become diverged from open source such that there's much fewer bridges, even though there's much more people in both communities than there were years ago. Do you have any advice for those of us trying to build those bridges, of how to build better bridges between the open source community and the academic computer science world?
Well, I don't think, I guess there was always been, some, I mean, I worked at Microsoft for, about 20, a long time, 20 some odd years. Microsoft is, very, very careful about, what we're allowed to, I wouldn't say, they're very careful about secrecy, not letting people know outside what was done. But Microsoft, and perhaps it was because, it started out, with a very different view of research probably than most companies. They always viewed one of the major goals of research was increasing this, was improving the science. And so, publishing papers was considered an important role. The work that I've done, I mean, my name is on a number of patents, but generally the stuff that I've done has not been of interest to industry until after the patents had run out. Basically because, I was working at the abstract level. And so, I think that there should be room, for, academics certainly should be working at an sufficiently abstract level, and that things are sufficiently far into the future that, they shouldn't have to get grants that, forbid them from publishing what their work is. But, things have, I think in many aspects in the world, and especially in this country, capitalism has just gotten to be much too powerful, and perhaps in areas of research that's maybe that's happening in research too. I don't know. Personally, I've been free to publish whatever I wanted because nobody thought it would be that useful in the near future.
So maybe time for one more, and then we'll call it a SCaLE. No? Oh, well.
Thank you for your talk, Dr. Lamport. It's kind of a two-parter. You talked about how you believe a problem should be strictly defined before you try to solve it by writing code. And in my experience, that's almost never done. It's rare that I ever see anything in a codified language like ASN1 or something defining a format or a protocol for code. So it must be enormously frustrating for you, and probably has been for a long time in your career, to see so many people doing it wrong and not defining it well. And you cited the example of the operating system that was written, the microkernel for the space project that was very strictly defined first, and they talked about how efficient it was. I wonder if you can talk a little bit about what it's been like dealing with the frustration of seeing people not do it right, and also Linux is 35 years old and it has about 40 million lines of code, and almost none of which has been done first through the strict definitions. I wonder if you can talk about how much more efficient do you think it would be if it was defined like that? So if you could talk about the frustration and how the efficiency.
You know, in terms of actual coding, my experience has just been pretty much, you know, the coding that I did, which I would say, you know, maybe started coding in 1957, and so it was only in, you know, probably the early 1970s when I did, you know, what I think would now be considered computer science, and so I was doing programming, and you know, I learned a lot of things, and it's really, the problem is that it's really hard to quantify, you know, what is gained. Matter of fact, you know, if you apply the method, if somebody, you know, if somebody is doing software engineering and are trying two different methods, or, you know, typically they'll try, you know, this method versus that method. What I'm arguing for would be considered cheating, because I'm saying, you know, don't go do the problem that, you know, that somebody tells you to do, that they think, you know, they want. Find out what they really need. And, you know, this whole, well, I want to get into the whole bit about agile programming, but basically, you know, it seems to be popular because programmers don't like to talk to customers. They'd much rather write programs. So, you know, that example of the virtuoso, you know, I think that's one, you know, the only example I know that, you know, could point of that to, you know, an example where you really have, you know, right in front of you, and the, you know, really dramatic results. But I can't promise that will happen, you know, the next time somebody tries it. But, you know, I've always found that I've never found that too much thinking has been a problem. And but I've seen that, you know, like I had an intern who, for a year, who was very bright, and basically he learned, you know, TLA plus, and he learned the idea of, you know, thinking and you know, specifying what it is you want to do before you do it, and then he got an internship, you know, another year, and, you know, the person who hired him said, "Stop writing all that silly nonsense. Just write code." So, yeah, thinking is a very hard sell. Most people would rather fight than think, and so, fortunately, I can have. The people I started, who first got interested in TLA plus, were hardware engineers, and they're much more receptive to the concept of getting things right, because they don't have the fantasy that, oh, programs are, you know, so easy, you know, are so malleable, you know, just a matter of writing a little bit of code, that they don't have to worry about getting it right the first time, you know. Doing it in silicon is, you know, it's a lot more incentive to get it right the first time. So, and programmers generally, never understand and realize how much work changing it will be, when it comes late in the design process. So.
Great. So thank you again for joining us and helping us close out the week here at SCaLE. And again, welcome to the SCaLE family.
Thank you.
Thank you.